Welcome back to the last session of the day. It gives me enormous pleasure to introduce my friend, Professor James Ladyman, who teaches the philosophy department of the University of Bristol and is the current president of the British Society for the Philosophy of Science. James is going to give a summary of today's proceedings. We'll speak for roughly 10 minutes, and then we have something like 10 to 15, 20 minutes for discussion. And I believe we have to finish roughly 5 o'clock. James.
Thank you. Well, thank you to all the speakers. It's been a fascinating day. I'm going to offer a few reflections and raise a few questions. So starting with Angie Hobbs's talk, Professor Hobbs has had to leave, so she won't be able to answer any of the questions that I ask, but perhaps you will. The issue came up there of the finite divisibility of space and or time versus the infinite divisibility. And I just want to make a couple of points about that. One is that we, I think, often confuse infinite divisibility with the continuum. And of course, that's not right. The rational numbers admit of infinite divisibility, but we don't have the structure of the continuum in the rational numbers. Now, that business of the reals being so many more than the rationals raises the question of the relationship between our representations of the physical world and the physical world itself, and whether the structure that we put into our representations is really in the world, or whether we've put a lot of extra structure into the representation to facilitate calculation or theorizing, even though the world doesn't have that much structure. Now, I think the jury's still out on these questions. So, of course, all our measurements are only ever of rational numbers. And mathematicians will tell us that the vast majority, the computable reals are measure zero in the set of the reals. So we have this strange situation where we're using vastly more structure to represent the world than we're actually able to encounter. So that's one point. And then the other thing that I thought was very interesting that was raised by her talk was this question of what, well, several themes that were picked up later. So one is whether space and time are somehow independent or existent, what their relationship is to material things. And that's, of course, still very much a live theme in contemporary physics, where there are people like Carlo Rovelli who insist that space and time should be understood as relations among matter in some way or other in the broadly Leibnizian tradition, versus those who think that space and time are existent in their own right and somehow independent of matter. And I thought the other thing that was very intriguing in what she said was the status of something like the instant of time or the point of space. You know, one might think, well, these things are abstractions. There's really no reason to be realistic about those notions, the notion of an instant of time. Now, I think Professor Hobbs didn't talk about it, but I think the modern answer to Zeno's paradox is essentially given by Bertrand Russell, which is to say, well, look, motion just is being at this place at this time and being at that place at that time and that place at that time. And as long as an object is at different places at different times, that's all there is to motion. There's no requirement that at an instant it's moving. On the other hand, if you think about how contemporary physics works, you might think to yourself, well, to really capture the connection between the states of things over time, we need something like a notion of instantaneous velocity if we're going to split things down into points of time. So maybe the alternative is to deny that there really are points of time, and then we won't need anything like that. There'll be no shortest units. The idea that ultimately somehow time is an illusion and everything is one Of course, we get some sort of correlate of that idea in the problem of time in quantum gravity, where with the Wheeler-DeWitt equation seems to suggest that there is no change at some ultimate level. So there's a sense in which I think that some of the questions raised by Parmenides are still sort of wide open. Is every way that we carve the universe up into separate things really an approximation based on arriving at an effective description rather than being some sort of ultimate division in reality? And I think that perspective is a helpful one maybe for thinking about ontology in physics, where the relevant thing is often that something counts as an object if we've got a description of the dynamics in the degrees of freedom of that thing that's effective at some scale. And there shouldn't perhaps be a further question as to whether or not those things really exist. So as if to say, well, all particles are like quasi-particles, right? Everything that we talk about in physics is something that allows us to write dynamics for a relatively separable bit of the universe, but we don't really think that anything's really separate in any ultimate sense from everything else, not least because everything's interacting with everything else gravitationally. There aren't really any closed systems, one might say. Good. Now on to fascinating talk about why the night sky is dark. And here, I don't think I have that much to say. Well, I know I don't have that much to say, apart from that it's interesting to observe how sometimes very simple questions have taken a very long time in the history of science to answer. And I think here of the question of the age of the Earth, which is also not resolved until modern physics. So who would have thought that we wouldn't know why the sky is dark at night, or indeed why the sky is blue without advanced theoretical physics of the 20th or even the 21st century. So what I thought was interesting in a way about that talk was that it seems to not rely upon anything that is that controversial or will be discarded by subsequent developments in future physics. So whereas some of the other talks are about the kind of foundations and maybe things could be very, very different, it seems like here we've got a solution to the problem that's going to survive whatever theory change comes along in future. It's all pretty well established from non-fundamental but well-confirmed physics. So we can chalk that up for the progress of science, I think, like the age of the Earth and why the sea isn't full of land, which is another thing that wasn't resolved until very late. You know, if all the silt is flowing into the sea through the rivers, why doesn't the sea fill up? Now, on to Maxwell's demon. And here I thought that some of what was said was a bit more controversial, so I'm going to pose some challenges. One thing I think that we should think about is the difference between phenomenological thermodynamics and statistical mechanics. And probably when we ask questions about the second law, maybe we should always say which version of the second law we are talking about, because otherwise you seem to get into kind of paradoxes that aren't really paradoxes. And before we get to Maxwell's demons, so if the second law and phenomenological thermodynamics are about systems that are at equilibrium, then we might talk ourselves into thinking that the second law is violated by fluctuations or something, right? Because we know that a system that's at equilibrium is fluctuating around that equilibrium. But I don't think we should really think of fluctuations away from equilibrium as violations of the second law, because the notion of equilibrium depends on the idea of fluctuation at some deeper level. It's not a violation of it, it's actually what equilibrium is an equilibrium in fluctuations. So the form of the second law that we have in phenomenological thermodynamics, I think it would be a mistake to say it's violated by microscopic fluctuations, because what the phenomenological law says is you can't build a perpetual motion machine of the second kind. You can't build a machine that will run a cycle whose sole effect is a conversion of heat into work. And I think that's, there are no violations of that. Nobody can build such a machine. Now, if you were to say, well, look at this Brownian motion. Look, that pollen grain just moved. That was work. The sole effect of that, we've got heat, we've got work from heat with nothing else happening. Well, I think then that's a misunderstanding of what's meant by work, because what we really mean by work is we want to be able to lift a weight whenever we choose. We don't want to retrospectively look at the movement of bodies and say, oh yes, that was work, I wanted that to happen. We want to be able to say in advance, when I choose, I'm going to be able to do this work. And it's that impossibility of us having a macroscopic, usable system that we can run cycles that will violate the second law. That's not threatened at all by microscopic fluctuations away from equilibrium. Now, entropy in the second law is used to explain lots of phenomena, not least in chemistry. And here I want to sort of pose a challenge for thinking about entropy in terms of uncertainty, which is just, how can my uncertainty about the state of a system explain why a chemical reaction takes place? Right? If there's the universe before life, there's nobody's uncertain about anything. Nobody's got any information about anything. There are chemical reactions happening because the state of the products has lower free energy than the state of the reagents. Well, if we want to be able to explain that using thermodynamics, surely we shouldn't have to appeal to the notion of uncertainty or what agents think about systems. So I think this is a familiar challenge that lots of people have raised to the kind of epistemic interpretation of probability in statistical mechanics. And one could go a bit further and say, well, look, when Boltzmann and Maxwell are considering statistics, they're not thinking about uncertainty, they're thinking about relative frequencies in large populations. And that's perfectly objective. There's nothing to do with people's beliefs or uncertainty or anything like that. Of course, the term statistics comes from the state, and Maxwell was explicitly inspired by the people who were gathering information about pensions and death rates and so on. Right? The statistics began with people trying to work out, well, if we're running a city, how much are we going to have to pay out in pensions in 10 years' time? Well, it's going to depend on how many people die in that period and whatever. And so that's where statistics came from. And they weren't thinking at all about uncertainty. They were thinking about objective properties of relative frequencies in large populations. And so I think the challenge to that sort of epistemic approach to statistical mechanics is just that, right? Surely we shouldn't be thinking about explaining physical and chemical phenomena with reference to agents. Okay, good. Now, another thing I think, though, that came out of the talk, which was really interesting, was this idea that we shouldn't rest content with sort of magical thinking in thought experiments in physics. So when we start thinking about Maxwell's demon, we should immediately think, how does a demon work? What's the physical process by which it's measuring? How does its brain work? And all the rest of it. Now, Maxwell himself thought that consciousness was separate to the physical universe, right? So there's a sense in which Maxwell believed in sort of magical thinking about demons, right? But if we don't, then we should never be satisfied with a kind of black box idea of the demon. And here we can make an analogy with Laplace's demon, which is a kind of similar type of magical thinking, right? You're told about this demon that somehow knows the positions of all the particles in the universe, but doesn't measure them, doesn't physically interact with the universe, doesn't affect them. Well, of course, if we get to a fine-grained enough degree of detail, then while I'm doing a calculation, the degrees of freedom in my head are going to be interacting with the system I'm describing. What we normally rely upon are the fact is that that won't make any difference, which it doesn't. But that's not, we can't appeal to that when we're talking about the exact fine-grained state of everything. And so one might then think, look, the idea of Maxwell's demon, Laplace's demon, it all involves this idealization. First, that we can separate off a part of the universe and call it the system plus its environment. And then that we can think about an observer kind of outside, not interacting with it, so on. But all of that is just an approximation. It's just for the purposes of some effective description. It's not going to be an ultimate fundamental fact about the separateness of that system. Well, about time travel, I just wanted to say tachyons on the standard definition go between space-like separated events. But if I want to time travel, I want to go into my past, I want to go back to a time-like separated event. And so I'd like to hear more about how that's supposed to work. I also worry about the intelligibility of scenarios based on using words and thinking that because we've said grammatical sentences, we've expressed a genuine possibility. So I can grammatically say something like, if I was a different person with different parents, would I still be here? Or, but those questions aren't meaningful, really. There's nothing, if I had different parents, would I still have green eyes? Well, you can say it, but it doesn't really mean anything, right? So the thought is that maybe time travel is like that, right? We've got a metaphor, really, about as if the past was a place, right? But it's not. I mean, time travel is between, you have to go back to an event, but you can't, an event isn't something in space that you can travel to. Of course, you also talk about going to your past, but if you're going to your past, then it's your future. So, what meaning are we supposed to attach to this idea? So that's that. And then finally, I'll just say, two thoughts about the last very interesting talk. One is it all relies upon unitarity, as was mentioned, and one could worry, well, look, unitary evolution is for closed systems. We don't have to think that it's fundamental. If we do accept unitarity, then you might think, well, then we have to have Everettian quantum mechanics and many worlds and all of that. And so one might think, well, maybe just, one might wonder, why are physicists so attached to unitary evolution being fundamental for the whole universe, given that we could only ever get evidence for it in some sub-part of the universe in some regime, effectively being subject to unitary evolution. And then the other quick thought I had was about what it would be to have a fundamental theory that didn't have space and time in it, and for that to be a quantum theory. And here I refer to my colleague at Bristol, Professor Mike Berry, who, when I always ask my students, what makes a theory a quantum theory? If we had a quantum theory of gravity, how could we tell it was a quantum theory? And one answer is, oh, it would have a non-commutative algebra. And another answer is, oh, it would have the superposition principle. And another answer is, oh, it would have discreteness somehow. And another answer is, it would have H in it, which is Mike Berry's preferred answer, because he's not a very fundamentalist physicist, although he's worked on a lot of fundamental things. He's a very kind of effective, messy, applied maths kind of physicist. And so, of course, Planck's constant has units that involve length and time. And so I was just wondering what the physicists who think that there's an underlying theory that gives us space and time, but it's a quantum theory, say about the units of Planck's constant. And I'll just stop there. Thank you.
Well, that was fascinating. We don't have a lot of time, and I think it's only fair if any of the speakers would like to reply to some of these interesting and somewhat provocative remarks. Yes?
You have Planck's constant. That's the fundamental thing. And then it turns out that the emergent thing that we call space and time just happens to be expressible in terms of that thing.
Right, so you said we've got the ingredients
the
of
other way
spatiotemporality by having Planck's constant, because Planck's constant has space and time in its dimensions.
Yeah.
Okay, yeah, fair enough. That's a quick answer.
I know that Jim wants to ask a question. Any of the other speakers who would like to? Jim.
Thank you. Just a quick quote, James, on the tachyon business. You say tachyons connects two space-like points. Going back in time just means you've got to jump to another inertial reference frame. In one frame of reference, moving faster than light. In different reference frames, it will look like moving back in time. But my question is, you commented several times about unitarity. The only system that's truly isolated is the entire universe. That's the only system where there's true unitary evolution. So my question is, our obsession with saying we're starting off with time reversal invariance, because all the fundamental dynamical equations of physics are time reversal invariant, and then we worry about how does irreversibility emerge from this, Loschmidt's paradox and so on. Therefore, isn't it the other way around? Couldn't it not be that irreversibility, an arrow of time, is baked into the universe? It's real, a la Smolin or whatever. And time reversal invariance is just an idealization. It's an approximation for isolated systems, which we don't really ever have within subsets of the universe.
Right, and you might think that about all the symmetries that we have. You might think, look, take time translation invariance. Any actual physical system, if you time translate far enough back into the past, well, there was no ordinary matter. So if you time translate far enough into the future, I don't know, maybe the Earth is gone, right? Now you can say, oh, that's just contingent, But still, one might think, yeah, but we're extrapolating from systems that are effectively idealizable as closed and separate from the rest of the universe, to which these laws apply, from that to the fundamental laws that govern the whole universe. And that, why is that warranted? Yeah, so I think I'm just agreeing with you. Yeah.
Any other? Could I just put in a plug for symmetries? I think it would be pretty dangerous in physics if we started to think that they weren't really fundamental. You mentioned time translation symmetry. Well, that's connected with the conservation of energy. Pretty fundamental thing. I'm not sure how much we want to play with that. Now, I know that in general relativity, it becomes much more complicated. But in quantum field theory, in the standard model and so on, conservation principles are very fundamental. And the reason that we got these theories is because we imposed symmetry principles on the Lagrangians, in part, in these theories. So I put in a plug for them. Any other points or questions?
Just a quibble. You said measurements are rational numbers. Surely measurements are intervals defined on the reals, and they're not even numbers, they're quantities.
Right, fair enough. I mean, all I was meaning was that when people write down the results of measurements, they write down some number that's been cut off somewhere. They're not right, or they put a number and put a little bar around it. Yeah, okay, fair enough. But either way, it's taking the representation massively seriously to say that a physical quantity has a specific real number value, I think, yeah. So I take that as a strengthening of my point rather than, yeah.
Yeah, over here.
You used the term phenomenological thermodynamics, but normally we just refer to it thermodynamics. Is that your philosophical look at
Oh, yeah. Sorry, so I just
thermodynamics?
So thank you. So I just wanted to distinguish between the theory that talks about, so for example, that people sometimes talk about the minus first law, which says a body which is either put in thermal contact with the environment or thermally isolated from the environment will reach an equilibrium state, which is such that there will be some set of numbers, which will, some degrees of freedom, which will characterize the body as a whole, right? So the classic being, say, pressure and temperature for a gas. And my point is just that's a different kind of theory to a theory that talks about a fundamental microstate or whatever, because the whole point about that is you have to wait an unspecified amount of time, and then the body is supposed to remain at thermal equilibrium for, well, a time that's long relative to the time scale of the kind of interactions that you're considering. So we think about something like a glass of water on the desk being at thermal equilibrium with the atmosphere. But of course, it's not really. If we waited long enough, the water would evaporate completely. So I think there's inevitable kind of coarse graining and an element of time scale, right? You have to talk about a notion, relativized to a notion of time scale to talk about equilibrium of a macro state. And I'm just drawing attention to the difference between that and thermodynamics and statistical mechanics, where somehow we're thinking about instantaneous microstates of particles.
So you didn't use it in the sense of a philosophical doctrine that seeks towards absolute...
No, I mean, I'm just meaning as well the difference between something like the Kelvin statement of the second law or the Clausius statement of the second law, which says you can't make heat flow from a cooler to a hotter body without doing work. Those statements, on the face of it, are different to the statement of the second law in statistical mechanics. And there's interesting relationships between them, but when we're being really careful in foundational context, I think we need to say which we're talking about, because the statistical mechanical entropy can behave differently to the thermodynamic entropy.
Folks, I think on that note, well, one last question is, as long as it's very quick, please.
Yeah, very quick. So I have a very quick comment on the Zeno paradox on the moving arrow. Do you think the Hamiltonian mechanics has two sets of variables, p's, which is momentum, and q's, which are positions? So they are separate. So for a moving arrow, you have the positions, but that doesn't mean you have definite momentums. So in modern point of view, the system are independent with each other, I mean.
Yeah, I don't know. I mean, but in that case, couldn't I describe it with Lagrangian mechanics and then you translate that into Hamiltonian description?
Or in Newtonian mechanics, if you want to get a trajectory of a point, you need two sets of initial conditions, which also are positions and the velocities. So if you don't only have positions and don't have velocities, you can't get the full trajectory.
Yeah, I mean, I was alluding to those complications. I mean, the symplectic manifold structure of Hamiltonian mechanics. I was kind of alluding to that when I'm saying it's, when I was saying maybe we do need to have instantaneous momenta. Because in that framework, they are defined at points, right? Yeah.
For those of you who don't know what the symplectic structure of Hamiltonian mechanics is, come back. Let me say, before I call upon you to thank all the speakers, I just want to remind you that today's conference has a special status. We're celebrating today, as Joe Ashbourne pointed out in the introduction, 10 years of a remarkable phenomenon in the public understanding of science, and in particular of physics and its history. And I think we should congratulate and acknowledge Dr. Ashbourne for her efforts and vision in organizing this whole project. So finally, my happy task is to call on you to thank all of the speakers today.